Hey guys, this is Mr. Reynolds here with the second lesson for diffraction. Apologies if you noticed the first time this video was done. Apparently I did not record the audio. Somehow that little button on my iPad got switched off. So this is my second try at explaining this second type of resolution. So hopefully this one works just fine. So we're talking about resolution. If you recall in the previous lesson, we saw that resolution was the ability to tell two different objects apart. We looked at Rayleigh's criteria. We saw that if you were resolving two things, you can see them as separate objects. Okay, so for example, look up in the sky, the galaxy, you see billions of stars all as one dot. You cannot resolve them. If you see a car driving down the road, you can see two headlights, and so you can definitely resolve those headlights. So resolution deals with the ability to tell two objects apart, two things apart. Today we're going to shift gears slightly, and we're going to look at resolution not of two separate objects, but instead resolution of wavelengths. Okay, so we're going to talk about the resolution of diffraction gratings. This is something very helpful, used a lot in science. As you go into your science classes in college, you will likely use this thing, what's called a mass spectrometer. And even next chapter in astrophysics, we are going to talk about how you can use, looking at the different wavelengths of light from a star, you can determine what's going on with the star. And diffraction gratings allow us to measure the individual wavelengths that we normally just see all as one. So I want to draw your attention to this image on the screen here first. We have white light coming in from the left, and it's hitting diffraction grating. So just a reminder, a diffraction grating is a film with many thin slits. We're talking several hundred or even thousand per millimeter. So a ton of tiny little slits, very close together. And when the white light hits that diffraction grating, the light is diffracted. Now we've seen in previous chapters, we've had equations, things like n lambda equals d sine theta, things like that. It's a lowercase d, sorry. We've had equations where we're able to tell at what angle the particular order, and would be our order, of wavelength is being diffracted. And we notice if the wavelength goes up, the angle will go up. And that makes sense here because look, red here's theta red and here's theta blue. Well, which one's greater, theta red or theta blue? Of course, it is theta red. Red is a bigger wavelength, and therefore it's going to have a larger angle. Okay, so we covered that in the previous chapter. Hopefully you're feeling pretty good about that. What I want to talk about today is looking at this situation, what we can do with it. You see, white light is a combination of many different wavelengths. Often, when all these wavelengths hit our eyes, we just see them as white light. But scientists often want to tell, well, how much red is there? How much of, let's say, wavelength 520 nanometers is there in that light? For next chapter in astrophysics, how much of wavelength 656 nanometers, otherwise known as the hydrogen alpha line, is there in that star? That actually gives us a lot of information and helps us figure out things like how old the star is, how big the star is the star moving away from us or towards us, how far, and how slow is it? Also, how far, basically, where is the star? How far away it is? I may have said that already. We can get a lot of information from this. So what we would do is we would send this light from a star through a diffraction grating. And we would set up a detector right here. Here's our detector. And there would be different spots in the detector. However much light hit position A right here, we know position A is where the red light falls and of whatever wavelength that corresponds to. And so we'd be able to measure how much of that wavelength there is. We could also put a detector B, and we could see, well, how much green is there? How much of 550 nanometers is there? And so we can use these diffraction gratings to tell all the different wavelengths of light. You can see another image here showing the same setup. You'll notice the top is a green laser, the bottom is a white light. Notice how the greens always line up. And we have diffraction happening. Obviously, this is n equals 1, n equals 2, n equals 3. And we can look at the different orders of diffraction from that diffraction grating. Now, here's where resolution comes into this. If I'm a scientist, I want to be able to tell how much of wavelength 600 nanometers is, as opposed to how much is in wavelength 605 nanometers, or maybe 601 nanometers. So for our purposes in this lesson, resolution is what is the smallest gap in wavelengths that I can distinguish. Just like in the last lesson, what is the smallest angular distance between the objects I can distinguish? In this chapter, we're talking about what are the closest wavelengths I can distinguish. If I have a wavelength of 601 nanometers and 600 nanometers, and I'm trying to detect those two wavelengths separately, can I physically do that? And this is sort of what resolution with diffraction gratings is all about. Can I resolve individual wavelengths, not individual objects? So that's sort of the shift we have going on here. Now, the equation we're going to be using is found in topic 9.4, and the equation says R equals lambda over lambda naught. Nope, sorry, I'm being silly. Over delta lambda equals mn. Now, I told you at the beginning of this chapter, you have really got to pay attention to the variables. Now, I've already had some people reach out to me and say, wow, it is sort of tricky to know which variable means what. That's definitely the case here. This equation especially sometimes messes things up with this m and n, because m means something we've seen before as n, and then you have another n, which is something we've never seen before, but it can be a mess. So please pay attention to how these variables work. So let's label some of this. Excuse me. R stands for resolvance. Resolvance is a term that basically tells how well can you resolve the wavelengths. A higher resolvance is good. A higher resolvance means I can distinguish smaller and smaller gaps in wavelength. Lambda here is wavelength. Typically, if we're looking at two separate wavelengths that are really close, we'll just take the average of them, and that'll be our wavelength. Delta lambda is the smallest resolvable gap in wavelengths. For example, if I had delta lambda equal to 0.5 nanometers, could I distinguish 500 nanometers and 501 nanometers? Could I measure each of those individually? Yes. Could I measure 500 nanometers and 500.25 nanometers individually? No. That gap is only 1/4 of a nanometer, which is smaller than the smallest resolvable gap. So I would not be able to distinguish those two wavelengths. Now over here on the right side, we have M and N. And this is where we can sometimes run into problems. M is the order of diffraction. This is the same order that we saw in a previous equation, n lambda equals d sine theta. In that case, they use a lowercase n. Now they're using a lowercase m. Thanks, IB. So over here on the right side where we see n equals 1, well, it also m equals 1. I think the only reason they changed that nomenclature is because they don't really want to have two n's next to each other. That'd be sort of madness. Capital N is the number of illuminated slits. Let me explain what I mean by that. So single slit has one slit. The light goes through one slit. It has one slit illuminated. Double slit down here has two slits. Light goes through both slits. 2 slits are eliminated. The more slits, going from 1 to 2 to 3 to 4 to 5, the more slits that you have illuminated, the more narrow and distinct your fringes become. The more slits that are illuminated, the easier it's going to be to tell this pattern compared to a very similar pattern that might be on top of it with a slightly different wavelength. So the more slits that are illuminated, the better the resolvance, the smaller the gap in the wavelength we can find. One other thing I want to point out is having to do with order of diffraction. Just remember this. Often we will not look at the first order. We will honestly often look at the second or maybe even the third, but usually it's the second. Anybody want to guess, why would we normally use the second order and not the first? The answer is the second order is spread out quite a bit more. Look at how far apart those different wavelengths are. It's going to make it easier to resolve those wavelengths. The first order, all the wavelengths are really close to each other. It's going to be really tough to tell them apart. But the second, it's a lot easier. The third is also nice, but you also don't get as much light going out of the third, and sometimes you run into, you just can't detect it. So usually it's the second, but the problem will usually tell you about that. So here's our equation. R equals lambda over delta lambda, which also equals m times n. Units, basically wavelength and delta lambda, these are in meters. If you want them both in nanometers, that can work just fine because they're just dividing one over the other. So you can use nanometers here, no problem. There is no unit of resolvance. It's simply a ratio. Order, no unit. Number of slits, no unit. But this is how the equation generally works. Right? So, we could look at an example type of problem. We could say, for example, let's see, what is the smallest gap in wavelengths? Resolvable with 500 nanometer beam light in second order with a 1,000 lines per millimeter beam. A lot of things here. And a beam of width of 0.25 millimeters. You can try this one on your own right now, and then we'll go over here in just a moment. If you'll hit pause. Hopefully you've hit pause by now and done that. So we're going to look at our equation. In this case, I'm just going to use the second two parts of that equation. I'm not asking about resolvance. If I'd asked for resolvance, you could solve for it. But lambda over delta lambda equals mn. In this case, we're solving for what is the smallest gap in wavelength. So that, of course, is delta lambda. So if I rearrange that equation, delta lambda equals lambda over mn. Our wavelength is 500 nanometers. Our order, it did tell us, is a second order. So we'll put a 2 right there. And n. N is the number of illuminated slits. Well, I know I have, different color here. I know I have 1,000 lines or slits per millimeter, and the beam is 0.25 millimeters. So if there's 1,000 lines for every millimeter, and we have a 1/4 of a millimeter of width of that laser perhaps, then that's going to be 1,000 times 0.25, and that is 250 slits that are being illuminated in this case. And that's what our capital N value is going to be. And this math is pretty easy. Delta lambda is 500 over 500. Notice I'm not even going to bother converting to meters here. I'm just going to say the smallest resolvable gap is 1 nanometer. So I would be able to tell 500 apart from 501. I would not be able to detect 500.5 and 500. Those would appear to be the same thing. I couldn't do it. So this is a resolution of diffraction gratings. Hopefully this equation makes some bit of sense. Again, please pay attention to what these variables mean. This is the toughest part of this chapter. Every individual equation is really not too bad. You just gotta know what all the symbols mean, because we've had M's and N's and capital N's, and M's mean other things, and this could mean N sometimes, and I understand the confusion. So please work at that. Please think about that. We will have our Zoom meeting coming up here, and so please let me know some questions. You have some book reading to do. I want you to do those worked examples, and then there is some homework about resolution, and hopefully that'll work out too bad. I think honestly the book work example actually made it onto the homework, so hopefully that'll be easy for you. This is Mr. Reynolds signing off. Hopefully y'all have a good and safe and healthy day.